Good morning. First, I would like to tell about my emotions a little bit. It's a great pleasure and honor to be here with you, and also it's a great pleasure to be recognized by Young Scholar Award of TASA. When I received the notification about the award, I was so happy, but my happiness was doubled because I received the email from Aydoğan Hoca. I was in college, I still remember his achievements about cellular phones, and he's using a kind of an imaging tool for medical diagnosis. And I was totally amazed at that time, and I want to say he's a great example for me, and I'm following his bright path. And I also would like to thank Haluk Hoca for his hospitality and the other people who made this event to be happen. My name is Canan Dagdeviren. I am a PhD candidate in the University of Illinois, Urbana-Champaign. I will tell you a device which is flexible, which can conformably wrap your heart, lung, and diaphragm, and create power and store this power to run the implantable devices such as cardiac pacemaker. This is the outline of my talk. I will briefly tell about background and motivation of my study, and then continue with results and discussion, conclusion. All my research based on piezoelectric materials, and these piezoelectric materials have an ability to capture mechanical energy from universe, such as heart beating or body movements, and convert this energy into electrical energy in order to power implantable devices, sensors, and even your personal electronics. But today's electronics are stiffer up to 6 orders of magnitude compared to soft tissue in human body. That's why there is a great challenge, a gap between these two concepts. For instance, my award is a wood form, and you cannot bend it because it's very bulky and thick. Whereas the same material, this paper, as it is very thin, you can totally bend it and even conform your arm or your tissue. As a material scientist and engineer candidate, I come up with simple and novel microfabrication techniques and tools which can allow me to use brittle piezoelectric materials, make them thin it down, and give me opportunity to have the devices in a flexible form to conform your heart, lung, and diaphragm. As I said, heart is not only an emotional organ. It's very complex as well, and it beats all the time, 40 million times in a year. It means a lot of energy. So you can wrap your heart with a device, which I have here, in a flexible form, which can be bended like that. And you can wrap your heart and get this beating energy and convert this energy into electrical energy to power the implantable devices, such as cardiac pacemaker. Today, patients need to change their cardiac pacemaker every 6 years because of the depleted battery. And once your battery is depleted, you have to open the chest, which means you expose the patient to the health risks and also additional surgical procedures, which is highly costly. So why we shouldn't capture our own energy and make self-powered cardiac pacemakers? So it was my dream. I made these devices on a silicon wafer because they have to sit down on a silicon wafer. They are high temperature resistive materials. And I fabricate all these things on this rigid backbone, and then use a polymer stamp which allow me to pick these devices and then print on a flexible polyimide, which is PI in that case. Oops. Sorry. And then, as we would like to use these devices in human body, animal body, we have to prove that these devices are biocompatible and there is no toxicity. So I grow red smooth muscle cells on the device and check over time and prove that there is no toxicity over time. And this is a little bit technical, but what I want to say here, in this slide, this is the in vitro results, and I talk with my device. I ask my device, if I bend you this much and with a certain frequency, how much voltage and current that you will give me so that I can move and continue my in vivo tests with the certain equations and device engineering the device layout. And this device can not only produce voltage and current, we can also store this energy. What I did here, I first imagined this cartoon where I have my piezoelectric device and a rectifier which can buffer the energy and a very small microbattery here. So when you check the voltage output of the battery over time, when you cycle it all the time, you can see this characteristic shape where it saturates around 3.8 volt, which is totally fine and enough to drive a cardiac pacemaker. And when you focus this small region, you could see this expected step size behavior in charging. When you bend it, it creates power. When you unbend it, again, it creates power all the time. So I affixes my devices on heart. I'm not sure how Burak Hoca found penguins for his slide, but I know penguins were so busy in Turkey last summer, so I decided to place my devices on cow and sheep. These experiments were performed in the University of Arizona Harvard Heart Center, and I work closely with heart surgeons. People generally call me Canan, but in order to make it's more good, they say Turkish lady. So in this case, I was working with heart surgeons, and they opened the chest and they said, "Is there any volunteer who wants to touch the heart?" I said, "Me, I want to do that." And after that, they call me from now on that time, fearless Turkish lady. So we affix the device on three different locations on heart, RV, LV, and free wall, to just see which is the best location to extract the power, maximum power. So we found that RV is the best because I studied heart so much at that time. It has a box shape, and it ejects the blood primarily by shortening its free wall, which bend the PZT, my device, more and creates more output. May you please click this red black thing? Yeah, you could see we place the devices on heart with the medical sutures. It's a very tiny rope, and it doesn't alter any, there is no extra load on the heart, and it's perfectly working fine, and there is no problem. And the other thing that we checked, we used how the heart size will affect the voltage output, because people are different from each other. Some of them are tiny like me, some of them are a little huge, so the strain will be different. So we checked which one is the best, and bovine is the best. And not only heart, we also place the devices on lung. The same thing, when you inhale and exhale, the power will be generated due to the respiratory force. And the last thing that we did, we closed the chest, because any long-term practical usage needs to be closed the chest. You cannot walk with open chest. So we closed it, and we checked they have the same capabilities. And also we placed the device, hooked the device with a cardiac pacemaker, and we show that it's perfectly working fine, and there is no problem. And as a conclusion, I designed and fabricate a biocompatible ultra-thin, first of its kind, which can generate power from the internal organs movement, and it can create sufficient power generation from your heart, lung, and diaphragm. And I thank my advisor, my collaborators, and also undergrad team. And as Berkin said once, the best sport that I do to run to future with my realistic dreams. However, now running is not enough. We have to fly, as the Twitter is banned in Turkey. So let's keep flying with our dreams. Thank you.